seem to slowly be, I have to come back here, even though I can speak up.
Okay.
We seem to be slowing down a little bit. And so we have asked Rob to present some of the data that he has. And you'll see that will undoubtedly elicit more comments. It's coming. There it is.
That's my teaching schedule.
Oh, okay.
So Rob Spencer from Florida State University.
All right, so this came up, I mean, it's come up a few times actually today already in terms of site selection. And so Peter kind of convinced me to come up here and talk to you about one of the projects. So we've been talking a lot about like land-ocean fluxes. And so for a long time now, we've been operating the Arctic Great Rivers Observatory, and I think this will be a useful thing to go through for delineating site discussion, which I think we're going to try and do in the morning. And so I'll talk a little bit about the Arctic Great Rivers Observatory. For those of you that are not so familiar with working in the Arctic, and I know at least one person in the audience has seen this talk before, so I apologize for that. I'll talk about why we care about Arctic rivers, where the Arctic watershed is, and kind of how hopefully some preconceived notions people have about that is wrong, and then characteristics of that Pan-Arctic watershed, and just general rivers that we work on. And riverine sediment, but it almost worked perfectly. And one of the big things that happened with talking with colleagues in Russia, we realized we had some great data in the US and in Canada, so in North America. And there was a lot of historical data held by Rosh Hydromet in Russia, but we were really concerned whether the data was comparable. Like, you know, were the analytical techniques they were using, both sampling protocols and then processing of samples, allowing us to compare the data. And so what it really set out to do was to standardize protocols and all samples are analyzed together in the same laboratories, and that continues through to today. And so that's actually maybe a useful thing to think about tomorrow as well with certain analytes, that this can be really quite painful in comparisons between labs. So samples were collected over multiple times per year and all phases of the hydrograph. And so I'll come back to this and why this is so important in, you know, Arctic fluvial systems. And so partners ran from 2003 to 2006. You can go to the website and check it out if you're interested in the data. And then Arctic GROW ran from 2009 to 2011. Arctic GROW 2 ran from 2012 through December of this year. And I'm happy to say, and I love my NSF program officers, that Arctic GROW 3 will run from 2017 through 2020. And so it just got refunded. And so, you know, this is serious baseline data that's available. You can go to the website, you can see who's involved. It's a lot of people that have been at Woods Hole in some point and are now all over the country or over North America. And all the data's there. And it's all freely accessible, and you can go in and download it, and you can access it, and it's all, a lot of it's published in various forms, but the raw data is there in Excel. It's really simple. There's a nice data interface. All you have to do is put in your first name, last name, and email. The only reasons we ask you to do that is then occasionally when we update the data, we'll email you and say, there's more data there now if you want to go and look at it. There's also all the discharge data for these big 6 rivers as well. And there's a lot of effort that goes into getting just the discharge data out of Russia. And so, yeah, the more people that use it, you know, it's great for everybody. So why do we care about Arctic rivers? And that feeds into a lot of the things that Paddy and other people have alluded to today. Why do we care about the Arctic so much, or land-ocean interfaces in the Arctic? Small ocean, big rivers, you know, it's about 1% of global ocean volume, and we have about 11% of global riverine discharge into the Arctic. And so, you know, I've heard my colleagues, Jim McClellan likes to refer to the whole thing as a super estuary. And so it's a really important land-ocean interface throughout the whole Arctic. We've done a lot of work looking at different traces across the land-ocean interface, and that's something that will hopefully continue through this project. And really, we like this idea of, you know, the mouths of these major Arctic rivers. We're looking at one site where we can take a sample and say something about processes and changes that are occurring throughout that watershed. You know, so if we're radiocarbon dating organic matter at the mouth of these watersheds, maybe we can say something about permafrost thaw at the, you know, that whole watershed scale. And so it gives us a very powerful tool. As we've already seen today, changes are underway. We've seen increasing riverine discharge, permafrost thawing, and then vegetation shifting, which we've not heard so much about today, but obviously imparts characteristics, especially on the organic phase, in terms of what's being exported between land and ocean. So I hope this is useful for thinking about this tomorrow, because we've spent a lot of time thinking about this over the last decade or so. And I've gone back and forth on this a little bit. In no ways are we saying this is the way it should be, but this is kind of where we are. So this is what we're currently defining as the one way to look at the Pan-Arctic watershed. And so this gray area here, you're looking down on the North Pole. And so this is basically all the water that's draining directly into the Arctic Ocean. It's about 15.5 million kilometers squared, and it's dominated by Russia. 3/4 of it is coming from Russia. Canada's got a good chunk at about 16%. Kazakhstan, that well-known Arctic nation, is at about 5%. Mongolia is at about 2%, and the US is about 2%. And this always shocks people. They love it when I give this talk in Moscow. It makes me really popular with my Russian colleagues. But you realize that these big Arctic rivers are draining really far south, all the way down into the steppelands of Central Asia. And then my Scandinavian colleagues have a little bit up here as well. So we often include this region as well, the Yukon. This water's coming up here and actually flowing into the Arctic Ocean. So if we include that, and this is our working definition as Arctic GROW, it's a little bit bigger, about nearly 17 million kilometers squared. Again, it's dominated by Russia, 70%, Canada, 17%, and then the US proportion goes up. But it makes you realize, Kazakhstan's still equal in terms of land-ocean export as the US. And so, it really depends on how you define this watershed and what questions you're going after. And so this is something we've thought a lot about with these big 6 rivers. And then the final way to look at it is to include this area here, which is going into Hudson Bay, but most of this water is coming straight out here into the Atlantic. It gets a little bit bigger. Canadians get a bit more excited now because they get a bigger share of the Arctic. Russia goes down, and really Canada comes into play, and the others don't really change. But we tend to stick with that middle definition. So when we think about this watershed, we think about the Arctic. Many of you work there. People who haven't been there often think about this sort of landscape, like this classic tundra landscape here. But really, when you look at where, this Pan-Arctic watershed, so this is sticking with that middle definition, see, tundra is really only covering a very, very small area of the Arctic. And so there's a huge amount of research that goes on in the Arctic, and it's focused on tundra systems. But, if you're looking at land-ocean fluxes, it's not the most representative landscape maybe to look at. It's only about 15% of the Pan-Arctic watershed is tundra at that scale. So the other thing we often think about is permafrost thawing, and I'm sure we'll talk more about this later today and tomorrow. But again, if we put that on the Pan-Arctic watershed, about 45% of it is continuous, a lot of it dominated by this area out into the Kolyma Basin out here in Russia. And then about 13% of it's discontinuous. And so still, there's huge areas of the Ob down here, the Sverania Divina and the Pechora, these big basins over here in Russia, the 7th and 8th biggest rivers in the Arctic. They're really, I think the Sverania Divina, if I remember correctly, doesn't have any permafrost in its basin, and it's the 8th biggest river draining into the Arctic Ocean. It's a real black water system. So, when we look at these rivers of the Arctic, we back up as a global perspective. We do a lot of work on rivers globally. So this is the global river ranked by discharge and the percent of global river discharge. So nearly 20% the Amazon. As we move, we see these blue dots through here are Arctic systems. So we get the Lena and the Yenisei, the Ob, the Mackenzie, the Yukon, and the Kolyma. These are the big 6 here that are all making it into the top 30. And so, when we look at those throughout the Arctic, you get a similar kind of figure. This is Arctic river rank now, not global by discharge, and then percent of Arctic total cumulative river discharge. And so the big 6, these 6 you can see here, are getting to about 65% of total Arctic river discharge. And that's why we really focused on them. For basically funding constraints and getting at 6 sites, we're getting about 2/3 of the riverine discharge to the Arctic Ocean. The middle 8, all of which I will add are in Russia. All these 8 rivers are in Russia, add you about another 15%. And I'll come back to this because there's some really important things that I think are key for us to think about for discussion tomorrow in here. And then when you start adding these smaller rivers, you can see you get very small gains in terms of cumulative, this is water discharge, but true for flux of most things as well. So 12 of the 14 largest Arctic rivers are in Russia, as I said, and so the 2 big ones that aren't, and I think we'll talk a lot about tomorrow, are the Yukon and Mackenzie. So when we look at area, this is that Pan-Arctic drainage again. The big 6 are getting you about 2/3 of the area, the middle 8 about 11%, so these yellow ones in Russia, and the remainder about 22%. And that's similar in discharge. The big 6 are about 2/3, the middle 8 about 15%, and the remainder about 20%. But when you start looking at watershed characteristics, when we start thinking about sites tomorrow, this is where I get kind of really interested in this. We've spent a lot of time working on these big 6 rivers. You get about 2/3 of discharge, but how representative are they of what's really making it out to the Arctic Ocean? And that's something I think we can address as part of this project, actually. If we look at the percent tundra, the big 6 are 1% tundra. The Pan-Arctic's 15%, because they're draining all the way south down here. The middle 8 are around 8%, and these remainder much smaller rivers, like up here on the North Slope, are much higher percentage tundra. And so we can start getting at how land cover is impacting what gets exported into these coastal systems. If we start finding higher organic matter yields from tundra systems that are up here than these big 6, then we can start refining our bulk scale Arctic fluxes to the ocean. Same for continuous permafrost. The big 6 are about 35%, but you can see that varies greatly from the Ob, that's about 2%, out to the Columnar, that's 100. It's the largest basin in the world underlain by continuous permafrost. But the middle 8 are about 60, and this remainder is about 73% permafrost. And so again, we can start doing space for time setups in which basins we choose and how that can then get into the modeling side of things going forward, potentially. So I'm not going to spend too long on this. I didn't actually know I was going to be talking today, but what is our current state of fluvial fluxes? And if you're interested in this, shoot me an email, and I can either send you about 40 papers, or I can direct you to where you'll find them all on the website. And those papers, a lot of them are things that we've not been involved with. We just get people to use this data and start improving these flux estimates. And so, many of you have maybe been working on, say, temperate systems, used to looking at discharge like this for the Mississippi, and you see, you get some spikes with big spring melts some year, big spring thaws, but you don't really see much of a change in analytes like DOC in the Mississippi. You may be getting a doubling, tripling in discharge, and maybe a doubling in a concentration of something like DOC. I'm an organic chemist, so I apologize, but everything I'll always talk about is usually organic matter related. If you look at these Arctic systems like the Lena, you see very low discharge under ice in the winter, then you see this huge spike in discharge, an order of magnitude through spring freshet, and it's a very sharp peak in discharge as well. And so at this time you have very high concentrations, typically in organic constituents, and very high discharge. So this is when all your flux is happening. So when I was saying earlier, we need to set a baseline for once this material is getting out into the coastal ocean, how's it mixing? How's that behaving? This is why it's so important to have seasonality in here. Because if we're not capturing late May, early June, I would argue in a lot of these systems, you might as well pack up and go home because all your annual fluxes are going to be way off. And it's very dynamic, It's going through this system where this is early May. You can see colleagues stood out here working on the ice from the USGS, and then sampling through ice. You have a couple of days like this through then to sort of normal characteristics late in the winter. And as I said, you're not just getting peaks in discharge, but you're getting big spikes in this case, dissolved organic carbon concentration through this time as well. Again, it's going through almost an order of magnitude in that case. And this becomes even more magnified on the smaller rivers or smaller systems that I think will be chosen for some of the sites for hopefully this project. And so all this is available. You can go in and choose whichever river you want to look at. There's nitrate data, silica here, and DOC, just chosen at random, plotted against discharge for the Lena and the Mackenzie. And so for the big 6 systems, this all exists. You can see, unsurprisingly, typically high inorganic nutrient concentrations in the winter, low organic concentrations of things like DOC. They spike in the summer as you get flushing of those active layers in the soil and the surface lid of vegetation that was fallen off the previous fall and then basically frozen in place, whereas you get dilution for the inorganic kind of analytes. And that's all broken out. Max Holmes has a paper a few years back where you can get into all the seasonality of it, and that's all readily available as well. One thing we've spent a lot of time on is improving fluxes of terrestrial DOC. And I think now, if I remember correctly, the flux estimates are about double or a little bit more than where they were 10 years ago. We've spent a lot of time looking at CDOM, so chromophoric dissolved organic matter, as a measurement to improve things for fluxes of DOC. And so across the big 6 Arctic rivers, see a fairly strong correlation. And then the same for biomarkers like lignin or dissolved black carbon that are tracing that terrestrial carbon. And so, you know, there's real potential here, and I think that will come to bear, hopefully, in Arctic colors for improving flux estimates and improving, getting at the fade of this material out into these marginal seas. So yeah, the new DOC estimates all sort of converge at around 36 teragrams or so per year, and you know, the old estimates were around 20. That's really come about by capturing that spring freshet period. You know, I mean, it's really important to get that, especially on the organic side. The new lignin flux estimate's about 168 kilograms times 10 to the 6 per year, which is double the old historical lignin load. And so for those of you that don't think about lignin as much as I do, or Peter does, I mean, we care about it because it's a very good vascular plant biomarker, right? So it's a great tracer of terrestrial carbon. Phytoplankton don't produce lignin, so if we find it in the Arctic Ocean, we know we're looking at terrestrial carbon. So this then gets really important, and this gets back to the kind of what Paddy was saying earlier about getting at mechanistic things, because we know then that DOC is transiting through either the Arctic Ocean faster, or if these higher loads are more representative, it means it's turning over much quicker. Because if you have a higher flux in, you know, your reservoir has not changed in the Arctic Ocean, then your residence time has to decrease. And so it likely highlights that this terrestrial material is more reactive than previously thought. And this is then backed up by, you know, bottle incubations that we do looking at biolability, as well as radiocarbon dating it. You know, we look at it and it's typically modern, it's fresh, and it's coming in off the landscape. And that all comes from an improvement in flux calculations. And so this is where some of these things can get really important, and some of the optical tracers can really help us as well. So we're thinking about the Big Six, and I'm guessing tomorrow we're going to talk quite a bit about the Yukon and Mackenzie. Much of the watershed that drains into the Arctic Ocean isn't Arctic. You know, you're starting really, really far south. And so we have potential here if we focus on maybe one or two big river systems, certainly maybe one, and then some smaller systems to kind of do space for time transition sort of work. And that could set things up very nicely for the modeling. The contemporary baseline, I'd argue, for the Big Six is now really well established, and thankfully we can continue to examine that going forward. That's part of a big NSF Arctic Observing Network project. And so we're now looking for this signal of long-term change. And we see that in the discharge, but we're now starting to look for it in some of the analytes. So we have enough data to start doing that. We have over a decade, and soon, hopefully, moving towards about 18 years worth of data. But this extrapolation to the Pan-Arctic is still really problematic. You know, if you look at those small watersheds, the last couple of years I've had a grad student working on the Spherinaya divina, and the DOC load from that system in Russia, the yield is 4 times greater than it is for the Big Six Arctic rivers. And so if that's more representative of those further northern latitude watersheds, then you end up actually nearly doubling the DOC flux to the Arctic Ocean from where we are now. And so we still are a long way off from potentially having a good handle on these numbers. And then the one thing that I think is really important to discuss tomorrow is the flux to the estuary. So where in the rivers, right, we're getting that flux to basically the last discharge station that we can get a good measurement on before we start getting any tidal influence. That's really different than the flux to the ocean. And so I am still, for the third time today, I'm going to say this, I'm yet to see any data across spring freshet on estuarine mixing. And that is a huge unknown in the Arctic that we need to get at no matter what you're interested in. And so I'm happy to take any questions and talk about this. And if you're interested in the data, it's either available on the Arctic Great Rivers website or through the NSF aoncadis.org as well. Thanks.
Thank you for that, because it emphasizes, you know, one of the comments that we've received frequently through the process was, why do you have such a large study region? And so the response is because it's extremely heterogeneous. And so the assumption was that most of you had had a chance to look at the science plan in order to be able to understand that. But here, I think it's being just brought to the forefront that that's what it is. And so it's not enough to look at even the 2 main rivers on the North American continent. And no, we've been strongly suggested that we only look at one and not really look at the smaller ones. And it's this balance, you know, between resources and what needs to be sampled. Questions, comments? Great.
So a comment would be that you don't even mention
Oh, it's absolutely mentioned in the science plan. Sorry, Greg.
Can I ask you a question?
Sure.
What's the relationship between your program and that other, the Global Rivers Observatory?
Yeah, so, I mean, it's all, so this is one NSF-funded program.
Right.
That's independent, it's its own thing. And then the Global Rivers Observatory is this, and then other river systems globally where we've either got some NSF funding or private fund, a lot of foundation money, and that's all cobbled together under one kind of umbrella. I mean, that's, yeah, I mean, the lead people involved in both of them are the same, yeah. But as it stands, actually all the products that have come out so far have been independent. There's not been, it's really only getting to the point where on the global river side, it started, Arctic Growth started first, and then it became the Congo and the Ganges Brahmaputra and then the Amazon, and I think now we still only have like 3.5 years of Amazon data, and we were meeting this morning actually saying, somebody should probably publish that, but no one's got there yet. And so, yeah, I mean, Arctic Growth was kind of the model, and but the nice thing is the analyses have all been done the same way across all those rivers now, and so the data's really intercomparable. It's all been collected the same way as well. So.
In the back?
Yes, I have a comment, and I'm like my colleague from UC Wilmington, I'm not doing that, not sure if you'd like to kind of get into it, but after your talk, it seems to me that we do have a very nice baseline of geochemical processes between river and coastal ocean fluxes, but the bio part is missing, is that correct?
Yeah, so 1 year there's like microbial composition data, but it's,
Right.
yeah, it's pretty thin.
They hear from Delaware,
Yeah.
from your
Yeah, and that was one of the things that's never been funded. The people who ran that kind of bootlegged it on, goodwill, basically, 'cause out of interest, I guess. But yeah, there's not a lot being done on the bio side, and as I said, there's not a lot being done downstream from the rivers. So I'd say we have a good idea what's making it to the freshwater seawater interface, and then beyond that, we have a pretty good idea. Maybe Dennis can speak to this about what's going on the marine side. But there's this big gap, between the true oceanography, like the blue water oceanography, and then I don't know what I am anymore, like the terrestrial riverine side.
So that was, it is, why we brought Arctic Colors, to understand that very dynamic transition zone that has both land and sea ice influences in there. And there is a baseline, there are data, but it stops before you get to the end of the estuary when all of those come together. Antonio, and then Lee.
Ross, what are the most downstream locations for these river water samples? Are they at a tide further out or further upstream?
It's the last downstream gauging station that's on these systems. I'm trying to find the map. I don't know if there's a good one on here.
Most of them should be above the tidal.
Yeah, they're all above tidal
Above
influence.
tidal.
I mean, this is probably the best place you can see it. I mean, so on this sort of scale map we look like, so Yukon's pilot station, Kolma's Chersky. So, you can get from Chersky out to the ocean, I don't know, it's like 5 hours on a small, sketchy little Russian boat. It's not that far. And so it's not very far distance-wise. It's maybe like 150 kilometers at the most.
What I'm trying to get at is those measurements from partners from HRO,
Yeah.
they'll be useful for scholars, but they're too far upstream.
Yeah, the pilot station data, if you're asking me, do I think things change between pilot and when it hits salt water? I would say no, actually, especially in the spring. The transit time's really short. It's hours. The only one that's quite far up is the Lena here. And that one's a couple of days, actually, from there to the ocean. And so, yeah, these other 5 gauging stations are fairly close to the actual estuary. On the Coloma at times, you see, so the other thing is in winter under ice, the salt intrusion can come really quite far up, and it will come as far up as Chersky on the Coloma even. I mean, I would say a much bigger problem, and if there's any hydrologists in the room, they can talk about this, is getting a good discharge measurement in peak discharge in these Arctic systems, you know? I mean, I've been there on the Yukon multiple years, and then the guys from the USGS turn up a couple of days later, because, you know, they wait and they come in. I mean, they're not going to spend a month out there. They're not, you know, they've got better things to do with their lives. So they fly in, and they're like, all right, so this is peak discharge. And I was like, actually, it was like there 2 days ago, you know? And they're like, okay, it's peak discharge. And then I'm like, what about all that water that's this deep that I can see 2 miles over that bank? And they're like, I don't know. If you tell me how I can measure it, we'll put it in. And I'm like, you can't, you know? And so I would say getting a really good peak discharge number is really difficult. And so then all your transit times and these sorts of things down to the estuary are hard. And the other thing to think about, you know, from what I've seen is none of these rivers have estuaries like I think about them. They have plumes that go out into the coastal ocean. You know, even in August, we were doing work on the Columnar. You know, we did an estuarine transect, and I use that term loosely, a salinity axial transect, I should call it. And, you know, to get a salinity of 1/2, we were 3.5 miles out the mouth of the Columnar. So.
Lee?
My comment, well, I wouldn't change anything that we need to do with the rivers and the constituents, but keep in mind that the amount of fresh water that flows through Bering Strait relative to the salinity of 13.8 Atlantic water is great. We don't understand the biogeochemistry whatsoever of Bering Strait. This is a big part of the story.
Yeah.
Over there? Yeah.
Yeah, that was great, actually. I really enjoyed that. And one of the things, I worked a bit with Deepwater Horizon spill. It got me interested in knowing how much carbon is added through oil spills globally. And it got me thinking when you showed the map of Russia and, you know, the big numbers there and the river discharge, that there's a tremendous amount of oil entering into the Arctic Ocean through river discharge in Russia, just through dripping of oil from pipelines. And I'm just wondering if that is part of the framework that's being proposed, if it's been discussed.
So this is something that's come up actually.
Here, come over here.
In the Gulf,
Sit.
sorry. This is something that's come up with colleagues in Florida through the Gulf of Mexico oil spill. So all I can say is that when we radiocarbon date dissolved organic material in the Russian rivers, it's modern. And so we don't see any evidence for a radiocarbon dead material there, which is always surprising to me, but we just don't see it. I mean, the amount of carbon coming off the landscape in spring thaw is phenomenal. And so it must be within background compared to it.
Yeah, I mean, it's like dripping, but some estimates, say from Greenpeace reports, they're quite high. It's like 500,000 tons of this stuff.
And the other thing that I can never quite remember where the Russian oil and gas is, but I think it's between some of the sites where we work. And so it might be much more prevalent in some of those riverine systems than where we are in the bigger ones.
Sure, and as a quick follow-up too, shipping, increased shipping, would that be something included?
You mean in the Arctic Colors
Yes.
plan? There
Yeah.
are comments to that in there. There are references, I mean,
Yeah.
to that as well.
I have homework tonight, believe
Yeah.
me.
So anyhow,